Hello and welcome to a quick introductory video into atom economy. Today we'll be giving you a brief introduction into what atom economy is, because it's mainly the crux of the calculations that you need to know for chemical synthesis. We'll be going over how this concept of atom economy fits into green chemistry as a whole in our video solely dedicated on green chemistry. So what actually is atom economy? The official definition is the percentage of the total mass of the reactants that are successfully converted to the desired product, right? In other words, how much of the reactant atoms or how many of the reactant atoms actually form our final product. And the most high yield thing you need to know is the higher the atom economy, the lower the amount of waste. A good little representation that I like to use is if you're a chemist and you're making a final product, would you rather use smaller blocks and create your product and have minimal to no waste? Or would you rather start off with a huge product and then make your slightly smaller product and potentially have a lot of waste? That's kind of the crux of the concept of atom economy. So it's focusing on the former rather than the latter. So I've got a little example here with carbon or carbon solid reacting with high pressure steam to give you carbon monoxide and hydrogen gas. And this is the desired product in the reaction. Now, that's not something you need to know, so I'll just label that as the desired product. So you don't need to know the desired product of every single chemical equation out there. In your year 12 exams, they'll probably give you the desired product for a particular equation, right? And you'll be asked to calculate the atom economy. So now let's apply our definition on the previous slide, and I'll just quickly clear. So atom economy is a percentage of the total mass of the reactants that are successfully converted to the final or the desired product, right? So what do we initially start with? I've drawn the schema. So on the left-hand side, we initially start with one carbon. So we have, let's keep a tally. We have one carbon, we have two hydrogens, and we have one oxygen. And the hydrogen and the oxygen form the water, and the carbon is obviously carbon in the solid form, right? In the desired product, we have one carbon, one oxygen, right? So that means two hydrogens, that's an apostrophe, two hydrogens have gone to waste. So the original two hydrogens that we haven't used. They've gone to waste. So how do we represent what we've shown, right? We've shown that originally we had one carbon, we had two hydrogens and one oxygen, right? In our desired product, we've only used one of those carbons and one of those oxygens, right? And we've left or kind of binned off two of these hydrogens. How we kind of represent this is through the molecular masses of each of the things, and that's what you're going to see in the next slide. So this is the formula for calculating atom economy. So it's a molecular mass of the desired product divided by the sum of the molecular masses of the reactants times 100%. Now we'll go over calculating the atom economy for the previous reaction on the next slide. However, there's something I just want to touch on really quickly. So just to recap, atom economy is the percentage of the total mass of the reactants that are successfully converted into the desired product, and that's kind of how this formula comes into effect. So it's a molecular mass of the desired product divided by the sum of the molecular masses of the reactants. And to really home in on that, what I'd like to do is go back to this thing here, right? So we have one carbon, like I said, and two hydrogens and one oxygen. And you can think of this as our original kind of building blocks in our Lego set, right? So we have one carbon, two hydrogens, and one oxygen. Our final building, if you like, contains only one carbon and one oxygen. So basically, what we're calculating in atom economy is the molecular mass of these divided by the molecular mass of all of these. So with this equation, that's exactly what we're going to do. So I've broken it up into a couple of steps, and I recommend you set up your working in a similar manner. So firstly, we're going to point out our desired product. So desired product, and these are our initial reactants. So for the first step, calculate the molecular mass of all the reactants. So we have our initial reactants are carbon and water. If you look at your periodic table, the molecular mass for carbon is 12. For water, it's got 2 moles of hydrogen, so it's 2 times 1.008 plus 16 for the oxygen, and if you add those two together, you get 30.027. Similarly, if you calculate the mass of the desired product, which is carbon monoxide, and I just want you to ignore this here for now, because that's just a blanket statement and it'll become a bit more apparent in the next slide, right? So calculate the molecular mass for carbon monoxide. It's 12.011 plus 16, so thus you get 28.011. Write out your formula, plug in the numbers, and you should get 93.3%. Now, how do we actually interpret this? So in our original reaction, I'll flick back, we had some building blocks, so 1 carbon, 2 hydrogens, and 1 oxygen. That had a molecular mass in total of 30.027. So that's what we started with. And in our desired product, we ended up only using 28.011. So 93.3% of our initial reactant molecular mass was successfully converted into molecular mass in the desired product. So that's a pretty good atom economy. So in the second example is where this kind of comes into effect. So multiplying the molecular mass of each reactant by its coefficient, right? So we have a reaction here. So we have methane reacting with oxygen, or 2 moles of divalent oxygen reacting to form water, which is our desired product, and I'll point that out, or 2 moles of water, which is our desired product, and carbon dioxide gas, right? Now we'll do the same thing. Initially, we start off with 1 carbon, 4 hydrogens, right? 2 oxygens, however, it's 2 O2. So we actually have 4 oxygens, right? So these are our initial reactants, or kind of like our building blocks, right? And in our product, we have 2 hydrogens and we have 1 oxygen. However, we have 2 moles of water that we form in the final reaction, right? So it's actually double of everything. So we have 4 hydrogens and 2 oxygens. So this is one way of thinking about it. You could find the molecular mass of this, so 4 hydrogens and 2 oxygens added together and divided by the molecular mass of this. So 1 carbon, 4 hydrogens, and 4 oxygens, right? So that's one way of thinking of atom economy. Another way that you can think about it is kind of like the working out that we've set. So firstly, calculating the molecular mass of all the reactants. So our reactants are methane and oxygen, right? So methane has 1 carbon and 4 hydrogen. So that's 12.011 plus 4 times 1.008. And in addition, we have 2 lots of O2. So it's 2 lots of O2. So 2 times 16 times 2. If you add it together, you get 80.043. Either way, you're going to get the same answer, right? It's just 2 different ways of thinking about it. Hopefully it makes sense. Our molecular mass of the desired product is water, right? So water is 1 oxygen, so 16, plus 2 hydrogens, so plus 2 times 0.2 times 1.008, sorry. However, in the end, we make 2 moles of water. So it's 2 times, open bracket, the molecular mass of the water, close bracket. And that's 1 water. And obviously, we have 2. So we need to multiply it, right? And if you put that into your calculator, you get 36.032. Again, write your formula. So it's the atom economy equals the molecular mass of the desired product. And you need to always take into account these coefficients, right? Because otherwise you're negating these initial building blocks, right? You're kind of missing blocks and you're creating things out of nowhere. So atom economy is the molecular mass of the desired product divided by the sum of the molecular masses of the reactants times 100%. Plug your numbers and you get a molecular mass of 45%, which is significantly lower than the previous reaction. So we need to improve this reaction. And I'll show you how to do that in our principles, in our video on principles in green chemistry.